Hello, everyone. Welcome back to our STEM Elementary course. And this class session is Math Rocks. And so in this session, we're going to take a look at an existing engineering activity with the three little pigs. And then we're going to transform that activity into a science activity or science inquiry lab and learn about the compaction and cementation process, also called lithification, of sedimentary rocks and how they form. And also we're going to weather those rocks away in an experiment to understand how sediment size and cement type can affect the strength of a sedimentary rock. And so the main purpose of this lesson for this class period is to see how you can also add a math application into the creation of an activity or into a procedure of a scientific investigation for your students, so they get practice applying those math skills that you're trying to teach them, as well as engage in the inquiry or scientific process skills. And so let's start by watching the Engineering with the Three Little Pigs video. This video comes from the article that I linked in your syllabus as part of the reading assignment. So you can get the full information on their version of doing this engineering activity, as well as having my tweaks that we'll be going over in the rest of this class period. Okay, doesn't that look fun? And it's so cute. It's a revolving around the story of the three little pigs as well. And so that's a really great inclusion of an engineering activity in the scope of a reading assignment or some reading activities that you probably already doing in your classroom. All right. So what do I like about the Engineering with the Three Little Pigs activity? First of all, I love that it's an investigation of ratios of sediment to cements. And so the water glue mixture in that activity is the cement, while the sand is the sediment. They use the same type of sediment and the same type of cement throughout, but they changed the ratios of them. And so I think that's a really great investigation. And since it's on ratios, we can turn that into something that could be an actual math application as well for students that are struggling with their fractions, percents, and decimals and ratios. And so another thing that I really liked about engineering with the Three Little Pigs was the use of the materials for the procedure. I particularly enjoyed their use of the paper cups. It was a really good size. In addition, it allowed for you to remove the paper cup from the rock after it formed, and so it was a lot easier to get it out, and it was less likely to break due to you trying to get the rock out of the container. And I really liked that they added the brick on top of it as a way to test out its strength. And so not only did they test the effect of weathering of the rock through a rainstorm, but they also just did brute force strength of the rock, and putting it in the mindset of this is going to be a building material. If we're going to make our house out of bricks, we also need to make sure that our bricks are strong enough for that purpose. And so I love that. And so what about including fractions, decimals, and percents? Well, we'll start with fractions. And so my idea for incorporating fractions into this wonderful activity is to get a hold of a transparent vial that is maybe made out of polystyrene or something that's plastic and easy to cut away if you want to cut it away, or instead of having to cut it away, you could pour it out of this container before it sets too long, and maybe you'll have a chance at getting it out. But in the event that it doesn't come out of the container very well, you could at least be able to take a little cutting knife for your students and cut them out for them ahead of time. But what you would do is take this vial and you would divide it. You could make one version where it's divided in half. You could take another vial, have a group of vials for your students where they're divided into thirds. Then you can have another set of vials that are marked in fourths and another set of vials that are marked in fifths. And so where are you going to get these vials at? Well, you can actually order some vials from Amazon. So these are 3 ounce, the same size as the paper cup. So that way, if you are able to, I haven't tested this out yet, but if you're able to, you could pour the mixture back into the paper cup. So that way you can tear the cup away if you want. Remember in the video, they sprayed the cup with cooking spray, nonstick cooking spray, to help it come out. You could also maybe try to line these vials up with like a petroleum jelly, and that will help the rock come out afterwards and keep it from breaking. And it also might make it easier if you're cutting it out also to keep it from sticking to the polypropylene, the plastic there. So these are pretty clear. There are graduations marked on these, but you can very easily take a permanent marker and mark these so that you have one that's particularly marked in halves, one that's marked in thirds, fourths, fifths, and so on. And so how are you going to do that? Well, to do it pretty accurately, you can just think about 3 ounces as the whole shape of the vial. And so if we have 3 ounces, that's 88.72 milliliters. So if you have a 100 graduated cylinder, 100 milliliter graduated cylinder, you could actually measure water ahead of time and use the water level to help you make your reference points for your students. And then of course you take the water out, let them dry, let your vials dry ahead of time, and then your students will have these apparatus already made to make the rock mixtures with. And so that would be, for marking it in halves, that'd be 1.5 ounces or 44.4 milliliters you're going to measure to make your mark. And so for thirds, calculated for you, that would be 29.5 milliliters per ounce. So you're going to do that for the first line, and then you're going to pour in another 29.5 milliliters to your second line, so that you'll have, and then you can put it in for a third line also, but it'd be just right at the top of the vial. So you would have this divided into thirds. And then for dividing it into fourths, that's going to be every 3/4 of an ounce. So that's 22.2 milliliters that you would pour in, make your line, pour in the next one, make the next line, pour in the next one, make the next line. And then of course that next one ends at the top of the vial. And then for fifths, it would be 17.7 milliliters per line that you're going to draw. And so that can help you make your markings so the students can see these vials as clearly parts of a whole. And so from that standpoint, then your students are going to have the opportunity to plan their experiment, right? You're going to tell them, well, we're going to test these different ratios of sediments and cements, or we're going to test our different ratios to make our brick mixtures even, if you want to stick with the Three Little Pigs story for the engineering activity. And so you're going to plan ahead of time the different ratios based upon fractions that you're going to mix together. So for example, maybe you want to have 1/3 of your rock have water, 1/3 of it to contain glue, and 1/3 of it to contain sand. So they would pour in, and there's probably a perfect order in which you want to pour these so that you can pour them back out of the vial very easily and get them into the bathroom cup or the 3-ounce cup, so that way you can tear that off and reuse your vials later in the future. And so I'm thinking probably sand first, maybe glue on top of the sand, and then the water at the very top so that it's not mixing with the sand or with the glue really well. And so you can then quickly pour it out afterwards, and then do your stirring inside of the paper cup or in another container, and then you can scoop it into the paper cup like you saw in the video. And so they could also, maybe they would have an opportunity where you're going to have them do fifths as well. Like you've got all the vials made, and so that could be 1/5 water. They want to use less water. They want to use 2/5 glue and then 2/5 sand as their ratio. Or maybe they want to do 1/4 water, 1/4 of glue, and that should not say glued. That should say glue. I'll have to fix that. And then 1/2 of sand. And so they would then, mix these up after they've measured them with the vials, and then they would have those mixtures made. And then they can run those tests of strength on the rocks that they made. Okay, so what about percentages? So percentages is going to be very similar. You have the same vials set up, and it's just going to be about how you provide the challenge to them. And so instead of them making their procedure with particular fractions of sediment, water, and glue, they're going to do it in percentages. Or you provide them with percentages, really, is probably the better thing to do. And so you, for example, would say, I want you to make a rock that has 50% sand, 25% water, and 25% glue. And so what they're going to have to do in these situations, they're going to have to convert these percentages into fractions and then reduce those fractions so that they can actually use these vials in order to make the rocks. And so, for example, if we have a 20% glue, 20% water, 60% sand mixture that they're going to have to make for their brick or their rock, then they're going to need to apply the point that 20% means 20 out of 100, and then I can reduce 20 out of 100 to 2/10. And since both of these are even numbers, I can divide by 2 and get the fraction 1/5. And so I'm going to have to put in 1/5 glue into my mixture. And remember, you're probably going to want to play around with the order in which you would put them in these vials. So that way they're easy to get the mixtures back out, and you can mix them in a separate container. Still working on this idea a little bit. So if you have suggestions or ideas about how you could do this, I would be super excited for you to actually make this a part of your product of implementation and try this out with kids. That'd be awesome. Okay, so now that leaves us with decimals. And so again, we're going to have the same set of vials that you're going to prepare ahead of time for your students. And then this time, students are going to measure with a graduated cylinder the amounts that they just want to use. Okay, and they can record those measurements as they make the rocks. And so from that, then you can tell them, well, now that you've made your rocks, while we're waiting on them to, completely go through this cementation process, while they're drying out and cementing together, I'm going to have you convert your measurements into percentages, or I'm going to have you convert it into a fraction so that we can use these values to communicate. Remember that numbers are also just as important as communicating meaning as words are. And so they need to be able to fluently interchange between fractions, decimals, and percents so that they can understand scientific reading where those particular measurements are reported that way, and they can also shift their measurements into the way that they want to use them for their reporting that will make the most sense for them. And so, for example, they may decide by making their rock that they ended up pouring 28.5 milliliters of water in. We got 10.9 milliliters of glue and 49.3 milliliters of sand. And so you put the limit, you can't go over 88.72 milliliters because that's how much that they can fit in these vials, because they're 3-ounce vials and 3-ounce paper cups that you might be using. And so by setting that standard, now they have an opportunity to do some math application here, some practice of their math skills. So if I'm wanting to figure out the percentage of water that's in my rock, then I'm going to do 28.5 as my part, and my whole rock is volume is going to be 88.7 milliliters. So I'm going to do 28.5 divided by my 88.7, and when I run the numbers, I get 0.321 as my decimal form of that expression. And then if I want to convert that into a percentage, I could do that as well, or I could leave it in the decimal form. But multiplying by 100 would give me 32.1% water. And so I can see students using these ratios, these percentages, to actually think about the results, right? So whenever they get the results from their experiments and testing to see which rocks held up for longer periods of time, maybe under the watering can, if they're timing how long it takes for them to crumble, or if they're timing how long it takes, or how many little bricks or little counters they could stick on top of it before it starts, crumbling. They could use these ratios in their interpretation of the data, so that they might see, well, these rocks that had more such and such in it did a better job at than the other rocks that maybe had more silt or more clay in it, right? Or more of the bigger pieces of gravel that were in it. And so they might find an optimal percentage. If everyone in the class is doing different percentages, then they are figuring out the best ratio or the best percentage of cement to sediment, or particular, if you're doing just one particular sediment, they would get that ratio for that rock. Okay, so let's talk a little bit more about the geology, because I keep mentioning rocks and how this applies. And so how does the science content fit into this, other than just the engineering activity? Yes, an engineering activity is something that you would teach in science as well, but we could also incorporate more science content knowledge if we wanted to, with using it in incorporation when we're learning about the rock cycle. And so the rock cycle explains these processes that a particular form of rock or matter, geologic matter, would have to go through to change into a different type of rock. And so if we start with magma, of course, all rocks, when they melt, whether they're sedimentary rocks, igneous rocks, or metamorphic rocks, they can melt and turn into magma. And so when magma cools, it begins to crystallize. And notice the only route out of the magma pool here is to an igneous rock. If a rock forms from the cooling and crystallization of magma, it is an igneous rock. And so it could then go through metamorphosis by putting more pressure on it, putting hydrothermal solutions in there and changing it into a metamorphic rock. You can do that. Sedimentary rocks can do the same thing. They can go through metamorphosis and become metamorphic rocks as well. And so those are two types of our rocks. And then our last rock is the rock that we're actually highlighting in this activity, which is the sedimentary rock. And so both igneous rocks and metamorphic rocks can become sedimentary rocks, but they first need to go through this process of weathering. So igneous rocks and metamorphic rocks are broken down into pieces through means of weathering, and then through erosion, which is the transport of these pieces to different locations, they then can become deposited, or this process here called deposition, where they are put in one place in common. And this oftentimes happens when water, like river, carries sediments to a particular place, and they drop out of the water because the sediments are heavier or they have less energy and they don't continue flowing with the water, and they deposit into these layers, right? And so deposition is required. You got to put your sediments in one place so that they can then go through the next process, which is lithification. And so, by the way, sedimentary rocks can also, once they're formed, change back into sediment by going through weathering, and they can then become sedimentary rocks. Again, that's very common. Um, so let's talk about the process of lithification, though. So first, we have to have weathering. Lithification won't happen unless weathering happens first. And so there are four main agents of weathering that a rock can experience. They're precipitation, wind, gravity, and weathering due to ice or glacier movement. And so in precipitation, weathering happens when rain, snow, sleet, or hail provides an abrasive force. So the just friction, grinding on the exterior of the rock or the surface of the rock, wears it into pieces, sometimes very small pieces of sediment. And so that's one way to make sediment. Wind is very similar to precipitation. It's instead using air molecules. So you probably imagine that air molecules are not as massive as, you know, rain or snow or sleet. And so it's going to take a longer period of time, or at least a stronger gust of wind, in order to provide the same amount of abrasive force in order for those exterior rocks to be rounded. And they become rounded because the exterior parts are broken into sediments, and then those sediments are carried away by the wind also and through erosion. And so that's another type of weathering. And then we also have gravity. And so this is like whenever you have an overhang or something where the weight of the rocks simply just supplies the energy. And so it starts bending under its own weight and breaking. And so then it will fall. And so as that rock falls, it hits the ground, and through that impact, it breaks into smaller pieces. So that's another process of weathering that forms sediment. And then, so yeah, there's a picture example of kind of weathering through gravity. And then for ice, we have frost wedging. Frost wedging is when liquid water gets into the cracks of rocks, and whenever it gets cold enough for that water to freeze, it freezes. And so the freezing of water actually causes the water molecules to expand, right? The hydrogen bonds and the shape of the molecule forces them into a lattice that's actually separated. And so there's there's less density, so there's more space between the molecules in that ice form than the liquid form, where they could actually flow in the liquid form and become a lot closer to one another. So that pushes the rock apart, and that rock then is chunked into pieces. So a lot of the potholes that we see here on our country roads in West Virginia are actually formed due to frost wedging that takes place. And so also glaciers are another way that ice can cause weathering to take place. And so glaciers are flowing like rivers, but instead of being water, well, there is some water at the bottom where ice is melted, but it's largely snow and ice. And so this is just moving through these valleys. And so the friction of the snow and ice rubbing against the walls of the valley actually causes chunks of rocks to fall off. And then they could fall onto the glacier and move along with the ice. Or from underneath the glacier also, they could pick up chunks and carry them through the glacier. And so that's another process of weathering. And I've found this really neat video, and I really appreciate the models that are demonstrating this. So we're going to take a look at this model of weathering by glaciers.
How do glaciers shape the landscape? Glaciers are frozen rivers of ice which have immense power. Glaciers are so powerful, they can carve huge chunks out of mountains as they flow downhill. This makes them one of the most powerful natural tools on our planet. Glaciers are sometimes called nature's bulldozer. Just like a bulldozer, glaciers shape the land in three ways. Firstly, glaciers pick up material. We call this erosion. Water flowing along the bottom of the glacier seeps down into the rock below. When it freezes, it opens up the cracks in the rock. This is known as freeze-thaw weathering. Then, as the glacier flows downhill, pieces of rock come loose and the glacier pulls them along with it. We call this plucking. Ouch. These rocks and stones scrape along the glacier bed like sandpaper, taking more rocks and stones along for the ride. This is called abrasion. Secondly, the glacier transports this eroded material as it flows downhill. Some of it is hidden inside or at the base of the glacier where it can't be seen, but sometimes it is transported on the top of the glacier. This is why glaciers often look dirty. As the glacier flows down a mountain, it gets warmer and starts to melt. Just like a snowman, anything which cannot melt is left behind. As the glacier melts, the rocks and stones fall to the ground. We call this deposition. By now, this material is a tasty mixture of rocks, stones, sand and clay, known as glacial till. The melted ice turns into meltwater and flows downhill to join a river or lake. Today, glaciers only exist in the coldest parts of our planet. But during the last ice age, glaciers existed in the UK too. Although the ice has melted, they have left behind some awesome scenery. As our planet warms up, many of our amazing glaciers are melting fast. So grab your walking boots and head to your nearest glacier while there's still time to see nature's bulldozer in action.
Okay, so lithification, once those sediments have been formed, they've been eroded and deposited somewhere, then they can begin the process of being buried over top of one another. And so that burial increases the pressure that's applied to the underlying sediment and allows them to be squeezed together. And that squeezing is the process of compaction. And then water contains dissolved minerals in it. And so whenever water is mixing in between those compacting sediments, they carry those dissolved minerals in with it. And so the water then can end up setting there and being stationary and eventually drying out. And so as it dries out, the minerals do not evaporate with the water. Instead, they precipitate out of that solution. And so they start adhering to the surrounding sediments. And that causes the sediments to stick together because they are sticking to the cement in between them. And this is the process of cementation. So lithification is both compaction and cementation together. And so this next video, I'm going to show you a version of this that you could do as well, another procedure and how you could do the rock activity. And so what I like about my particular video is students get the experience of compacting a rock and putting the cement together rather than just putting the cement in there, which is what we would see with the previous procedure. Because we're going to use this syringe with our rock mixture, we're going to compact it together. And so that's true lithification and formation of a sedimentary rock. And so that's what I like about this version of the activity. And so I'm going to play this and you'll see a couple of different examples of things that you can do in addition to the Three Little Pigs engineering activity. And so from that, you can decide how you're going to implement this in your classroom.
First, we need to prepare the syringe, and any type of syringe will do. This is just what I found in the stores. And so what I'm going to do first is I'm going to seal the bottom of the syringe. Typically I would use modeling clay, but I didn't have any around the house, so I'm going to put this thumbtack in and tape it down. This is just to keep the water and the sediment from coming out whenever you compact it. Find 2 or 3 different types of sediment with different grain sizes. Play sand works well. I'm also going to use kinetic sand this time, and I found this coffee facial mask that was really interesting, so I'm going to try it too. In the past, I found a facial clay mask that works as a silt-sized sediment, and so I couldn't actually find that this time, so I'm hoping the kinetic sand will serve that purpose. make different ratios of sediment in your rocks. And so I'm going to divide everything off into thirds. So I'm only going to use the 15 milliliter mark. And so for my first rock, let's try a third of each sediment. So I've put in up to 5 milliliters of the play sand, 5 milliliters of the kinetic sand, and now 5 milliliters of space for the coffee facial mask. Now, for students, I would probably use a permanent marker and prepare this ahead of time and mark the syringe off into thirds. But this will do for now. So I'm going to take all the sediment now, dump it into a cup, and mix it together. But I also need to add the cement. So I put in some water to serve as the cement. And water works well as a cement because it carries minerals in it that are dissolved. And so as it evaporates, it leaves the minerals behind. And so they become the cement that glue the sediments together. Okay, so now I'm going to use some petroleum jelly to lubricate the syringe walls. And this is just to help the rock, once it's been compacted together in the syringe, to just kind of slide out. And that way I can set it on a paper plate or a paper towel and let it dry for the rest of the evening. Okay, once your sediment has been mixed up, you're going to pour it all into the syringe. And then you're going to take the plunger and insert it back into the syringe, seal the top on it, and then you're going to compact the sediment together. So we've added the cement, and now we're going to compact it together. This is the process of lithification. Lithification involves both the compaction and cementation of sediment together. Spend some time actually compacting the sediment together. The more that you compact it, the stronger it's going to be whenever you try to get it out of the syringe. And so be careful. You could, if your fingers are, slick from messing with the sediment or the petroleum jelly, you'll slide around. And so you want to make sure you have a really firm grip on your syringe before you start trying to squeeze the sediment together, or you could really make a mess or even hurt yourself. Okay, let's see what happens now that we've compacted and cemented the rock through the process of lithification. And I'm just going to tap the walls of the container and let the rock kind of work its way down through the syringe. And it's best if you wait a little bit for it to dry out before you do this so it doesn't fall into pieces. I probably could have waited a little bit longer on that. Okay, this rock, we're going to do 2/3 play sand to 1/3 coffee facial mask. Here we go. Wow, this is mixing a lot better. Because I didn't put a whole lot of water in the mixture, just enough to help it get moist. Wow, that rock came out of the syringe much better. Still maybe a little bit too wet. I could have left it in a little bit longer, but we're going to have it sit on this paper towel and dry overnight. Okay, so here are the different rocks that I made. And so I'm just going to leave them out to dry over the evening, and then we're going to test them out afterwards. Okay, so I just moved outside and set these down on the table, and you can see already just by putting them on the table which ones are weaker and more susceptible to weathering, especially weathering by gravity, because that's all that happened here. The rocks kind of dropped just a little bit when I set them on the table. And so next I'm going to test them according to being weathered by the wind. And so I'm just going to reposition the camera, and then I'm going to blow on them a little bit, and we're going to see how they respond to being weathered by just a small breeze from the exhale of my breath. Okay, and you probably noticed that the rocks that were weathering already due to gravity were more susceptible to being weathered by wind as well. And you could see how wind also plays a role in erosion. Those sediments were then transported somewhere else. Whereas these rocks that are more resistant to weathering are still sticking strong. So that means I need to test them out by precipitation. So I'm gonna fill up my watering can and see what happens. So just need a minute and we'll be back. So I decided on a cup of water rather than a watering can. I don't really feel like getting super wet. So this rock here made of just the kinetic sand. Of course, there's just a little bit of sand particles that were left behind in the syringe when I was making this, but this is the 100% kinetic sand rock. Let's see how it holds up. Wow, I've entirely flooded the plate that it's on, and it still hasn't broken down. I'm going to directly pour here on this. This is the 1/3 face mask mixture and the 2/3 play sand mixture. Very easily weathered by water. And this is the 100% face mask mixture. Also easily weathered by water. And I'm out of water. So we'll be back in a second and we'll check on these last two. Okay, I'm back with another cup of water. And this time we're gonna start with the rock that started crumbling a little bit under its own weight due to gravity whenever I set it down on the table earlier. And so we'll start with that one. That's the 1/3 face mask to 1/3 sand to 1/3 kinetic sand. And you could tell that the kinetic sand is holding strong here. Okay, now let's try this. This is the 100% play sand mixture. Oh, crumbled instantly due to water. Okay, so that's the results of the weathering portion of the lithification lab.
Okay, so as you can tell, the kinetic sand was really good at holding up to weathering, and I believe that the reason is because the particles in it are made smaller, and so it's a smaller grain size of sand than what's in the play sand. Plus, it's kind of moist, and so what I didn't like about using the kinetic sand was putting it in mixtures with the other sediments, because it was not mixing very well. It liked to stay to itself, and so for that reason, I don't think I'm going to use kinetic sand again for this activity. I learned that this time. And instead, what I would use would be an actual dry clay facial mask that you would have to mix with water in order to use it. And so I've used this Aztec Secret Indian Healing Clay before. It's not too expensive for a whole bunch. And you can get that on Amazon by clicking the link here. And so it's a clay-sized particle, so it's a smaller sediment. And then you could also just use your regular classic play sand for your sand-sized sediment. And if you want something a little bit larger, that coffee bean or that coffee-flavored mask that I use actually had larger pieces of sediment in it. And so I did like that sediment. Would use it again since it mixed well with other things. But you honestly only need two different size sediments, two clearly different size sediments, because you could do a fraction of this, a fraction of that, and then also you have a fraction of water that you can incorporate into this, even though you really don't need a whole lot of water. You just need enough to moisten it. You don't want to use too much. If you use too much, then there's no way you're going to form a rock. And so you could make a water glue mixture like they did in the engineering pay activity, and then use that as the other piece of this. That might help keep your rock firm rather than just kind of being flushed away whenever you're trying to compact it. And it's not going to, the water's not going to mix as well with the sediment if you use too much. And so those are some suggestions on sediments that you could use, and incorporating them into that fraction decimal percentage activity. And so I would do that. That's what another change I would make to my activity is. I know I use the syringe that had it marked in milliliters, and that's something that I would definitely be doing with my high school students and have them figure out their own ratios. But when we need to guide our younger learners, we need to make this a little bit simpler for them. And so we need to make a device that doesn't challenge them by how they are reading it, right? They can just read these markings, and that would be plenty, so they get practice on their fractions and percents. Now, if you want to use the syringe and measure things by estimating, one place value after the marking, that would be great. You could do the syringe for that. But I also think that filling the entire syringe is not going to give you a really good rock, because you're not going to be able to push on the plunger very well. So you're going to have to help your students visualize their fractions differently. Whereas if you use this vial before you mix it, this allows them to see a whole and then the separate parts, and then you can put it into the syringe and use the plunger. And so this could be, you could program it so that your vial that you're using with the marks are smaller than the actual syringe that you're using. So that way it doesn't fill the whole syringe. So again, the 3-ounce syringes are good for mixing with the paper cups, and here are the equivalencies so that you can make your markings for the halves, thirds, fourths, and fifths. And I would have students plan their rock mixtures ahead of time and then prepare them once you've approved them. And so again, same slide as before. Just I would also do that in the scope of the geology version of the lab, where you're teaching those vocabulary terms of lithification, cementation, weathering, compaction, erosion. All of that is a good way to stage the activity as well, not just the engineering with the 3 little pigs. And so what I love about the activity is students get the application of math, but then they're going to use their results, right? And so part of the results are going to be the percentages that they tried and how good they held up to water, or how long it took before they were broken down completely with water, or stacking a brick or stacking something a little less heavier than a brick and continuing to stack it on top of it. Help them measure the strength of those things, and then they would have this opportunity to interpret information and come up with a conclusion, right? They're going to say, well, I noticed that the sand has longer pieces or has bigger pieces in it than the clay mud mask, right? The clay mask. And so the clay one stayed together a lot better. And so the reason could be because then they were going to come up to this idea that the reason could be because of the size of the sediment. And that's very true. There are different size sediments and sedimentary rocks, clay being the smallest size. And then between clay and sand is actually silt-sized particles. And so those exact measurements here are reported in millimeters. And then sand, and then I had a coarser sand, a very coarse grained sand size with that coffee facial mask. So you can get different types of sands even. It doesn't have to be, you don't have to have silt. Like I in my experiment, I didn't include silt at all, but you could still get different types of sizes. Pebbles and boulders are also sizes in sedimentary rocks. You'll notice that these rocks actually end up weathering faster than rocks that have a larger percentage of smaller sediments in them. And so this is just an image of the soil triangle. And so it shows how soil is made up of 3 types of sediments: clay, silt, and sand. And the percentage of those actually determines the type of soil that you're going to have. You're going to have a clay loam, a silt. And so silt obviously is going to turn into a siltstone, sedimentary rock. Clay is going to turn into a claystone, sedimentary rock. Sand is going to turn into a sandstone, sedimentary rock. And so you can actually have a mixture of these small particle sizes and get different types of sedimentary rocks. And so another difference in sedimentary rocks is the percentage and type of cement that you have per sample. And so common cements for true sedimentary rocks are silica, which is quartz or SiO2, calcite or calcium carbonate, and iron oxides. And so also the cement lends into the strength of the rock, not just the percentage of it in the rock, but also the composition of it, right? Some agents of weathering can cause these cements to react and decompose, right? Carbonates are very susceptible to weathering and acid precipitation. Acids react with the carbonate and break this down a lot faster. And so you'll see a limestone, which has a calcite cement in it holding the sediments together, are more susceptible to chemical weathering than they are mechanical weathering. And so that's another thing that your students are going to be able to analyze based upon their results. And so just think about students looking at that data, thinking about why this rock did better, and coming up with their conclusion based upon just the information available to them and their experiment. And they're already starting to discover this information, right, without you teaching it to them. And then you can use this as an opportunity to open up this lesson on different types of cement, on different types of sediment sizes, and the different types of weathering. So it's going to be a really great way to introduce the topic in geology if you do it this way. Nice exploration lab. And students, again, get to practice those science process skills, and they get to work on the integrated process skills as well in developing their experiments. In this one particularly, they're developing their procedure by deciding the ratios of rocks that they're going to actually test, which is their independent variable. So I'm pretty excited about trying this out. I hope that you guys really like this activity, and if you've never tried it before, I hope that you try it. It's going to be an amazing addition to your classroom. So thank you guys so much, and I really look forward to seeing what you guys come up with. So I hope this helps you get another example of what you can do for your product of implementation. All right, see you guys next time.